Howdy, calculus. We are going to take a look at linear approximations today. And so, one of the weird things about linear approximations is it's basically asking you to come up with values of functions that are approximate instead of exact. So this is kind of a puzzling thing, I suppose, to wonder why this would be important. Because as I have at the bottom there, when you have computers, even if the function is pretty nasty, you can just shove the value you're interested in evaluating into that function and try your best to be patient as the computer chugs through it, which usually in most cases today wouldn't be very long for any sort of function that you would be interested in. So why would we care about approximating these things? Well, the truth probably comes more from not asking a computer to do this once, but asking a computer to do it a million times, or a million times a day, or a million times an hour. And if that's the case, where you are doing something repeatedly over and over and over again, and it takes up a reasonable amount of computing power, when you do a linearization, you are approximating the function as a line. And if you're approximating it as a line is a very simple thing to calculate. So it's got the coefficient on the value you're putting into it. So there's a multiplication. And then there's an addition or subtraction, depending on what if you say y equals mx plus b, what the b value is. So that's all that has to happen. So two operations are going on, no more than that ever. And so it's a fairly tidy, quick calculation, and might be significantly less computing power required than in one that is a function that's much, much more complicated. So it may be that you cut a corner a little bit by using an approximation, and you get values that are reasonably good as long as they're within a certain window, and those are good enough for whatever it is that you're doing, and it saves time or computing power, depending on what else you're doing at the same time with the computer that might be important. So it's still something that is currently used, even though it seems like it would have been better when you needed to do things by hand and you just couldn't evaluate these nastier little functions as nicely. So first of all, what we're basically doing is, if you can see it, which it's kind of harder here, I'm going to use my highlighter and go over top of it, but if you can see this thing right here, it's our original function. We're just going to call it f of x. And so let's just say that there's a point right here where I can very, very, very easily evaluate what f of x is. Now, there's these points on most functions. So even if you are not good at evaluating, for instance, sine x at every particular value, which would be pretty reasonable, you probably can evaluate sine x around 0, or at 0, not around, at 0, because sine of 0 is 0. And so you know that one, it's an exact value, it is perfect at that particular point. So let's just say that that little dot that I made is representing a place on this function where I know how to calculate this value quite nicely. Now, technically, you don't need to know how to calculate it in order to make linearization, but it's not very useful unless you do know the answer to this particular value. So once we're there, what happens is the function curves up like this. But what I'm going to say is that, what if the function didn't curve up, but instead just increased linearly? So it just went along that line instead. As you can tell, these are awful highlighters that are like super wide, but as you can tell with the bleed over here, as I kind of tried to make it, well, it wasn't even very centered, but that's all right. The closeness maybe of the curved function f of x and the linear function that's down here, they're very close and similar at values that are close to f at a. That's because this function, like all differentiable functions, would exhibit local linearization. So if I were to zoom way in at f of a, it basically looks like a line anyway. The further you get away from a, the more that slope is going to change, but in values that are fairly close to a, it's a reasonable approximation. If you can see it, which it's kind of hard right now, but there is an f of x here that is on that particular function. Man, I'm going to go big one. So f of x is right there, and so right below it is the value right here on the line at that same x value. You can tell that there's a little gap between them. They're definitely not the same, but it's not real bad. If I were to go out here and I looked at this value versus this value, that's not very good. So that linearization is going to be not helpful, really. It's it's a value of somewhere around 20 versus it's supposed to be a value around 11. Other way around. It's going to give you a value of around 11 when the actual function would have been a value more like at 20. So that's just not going to be very useful there. So one of the things you have to remember about a linearization is they are only good very close to the value. So there are, as we'll see in a moment, there are some different things that you can do linearizations for and use them to evaluate. But the further you get away from the point that you did the linearization around, the worse your estimates are going to be. So down here I had this little thing that now we got all this lovely little color all over this. Let's see if I can get rid of it all at once. No, I guess it doesn't do gestures, or maybe it does, but I might have messed it up. All right, so what we're going to do is we're going to say that at that value right there, we are at f of a. What we want is we want to estimate the value here by using the value here instead. So how do we get that value on the line? Well, if I said that value, sorry about that. So I'm going to use a line here and just say that there is a horizontal level right there where we have f at a is the value there. So this particular spot right here is vertically above that line. And if we could find out how high above f of a it is, then we would have the answer to the approximation of what f of x is. So it's f of a plus whatever the height of this dotted line is right there. Now, you probably can tell that that's a part of a triangle. So if we just kind of bring a little bit of highlighting to that triangle that I'm talking about right here. So let's bring it over here and just talk about what the different sides of that triangle are, some different things about it. So there's a right angle. A right angle. Let me do it that time. No. Okay, I'm going to do it as two different things. A right angle in that corner of the triangle. So it's a vertical y distance that we're wondering about versus that x distance. Now, the this thing right here, the x distance, is basically the length along between those two x values, which is x minus a. I'm going to have to do it on my pad. I didn't realize how awkward that was going to be. My apologies for that. So I'm going to switch over here, and we're going to go. And so this part down here is x minus a. Because if we look at the second point is at x comma f at x for the original function, but that top corner of our triangle is at x comma, I'm just going to put question mark actually for now. So I don't know. Things are just not working so well this morning. So it's at x comma excuse me, x comma question mark. So the bottom would be at the same x value underneath the part that's lined up, and so it's x minus the original value that was there along that x-axis, which is a. So that's x minus a long. So now we can describe the slope, rise, and run of those 2 points by just saying slope is equal to rise over run. Now this is a really weird thing because I labeled that with a question mark. I'm going to actually relabel that with an H just to represent height for the time being. So that actually would be at f of a plus h. So it's just going to be up in the air a little bit, but I'm just going to call it h for the time being. So my slope value is going to be equal to the rise of h over the run of x minus a. Now, that slope of the linear function there is actually the same as the slope of my original curve function at a. So it's the tangent line. that's what this linear function is. So since it's the tangent line, its slope is going to be equal to the derivative of f at a. What's the derivative of f at a? Well, it's just f at prime at a. And that's going to be equal to h over x minus a. Which means that that height is equal to x minus a times f prime at a. I squeaked a look up there just for a moment to see which order I had written it up here, so it was a little more in line with what I was doing there. So it's going to be f prime at a times x minus a. So what do we get in total? Well, the value of the function at x is about equal to the original horizontal line location, which is at f of a, plus the height change, that side of the triangle, which is f prime at a times x minus a. All right, so basically what that means is we now have a linear approximation for any function centered around a. So this is going to be reasonable as long as we are relatively close to the value of a. So if this a, which on ours over here, appears to be at about 1.5, so it seems like somewhere around 2 or a little bit before 2 or even somewhere around 1, both sides there, those are going to be okay values. We're going to be able to get numbers for those that kind of make sense. If we were to try to evaluate what's going on at like 3 or negative 10, that's going to be complete garbage. So linearizations are only good close to the value that you're centering it around. Now, we can pick the centering value. So if you're doing these by hand without a calculator or a computer, you want to pick something for the a value where you can evaluate f of a easily and hopefully evaluate f prime at a easily. But we just want to make sure that that is the case. So we'll go ahead and try this out with some different functions. So the first one I'm going to take a look at is the sine of x. So this is actually something known as the small angle approximation is basically what we're going to come up with. It's for sine. It's pretty neat. So we have an original function. Woo, wrong thing. We have an original function, f of x, and it's equal to sine x. And I want to approximate this thing at roughly at 0.1 for the x value. So we're going to say that the value of f of 0.1 is approximately equal to, and we need to pick a value close to 0.1 that we're comfortable with the sine, the value of sine at that spot. It's really close to 0. We're comfortable with that. Sine of 0 is 0. So let's go ahead and say that according to what we just said, it was the horizontal location at that point we're comfortable with, which is f at 0, plus f prime at 0 times x minus 0. Now this x is actually 0.1, so I should probably fill that in instead of putting down an x. So let me do that. 0.1 minus 0. Otherwise it's awkward because there is no x on the other side of the equation in function notation. So that's good. That's our approximation. Now, because we want to be able to do this by hand, first of all, the things we need to know, sine 0 is equal to 0. I do need to know the derivative. So f prime at x is equal to cosine x. And so f prime at 0 is equal to the cosine of 0, which is 1. So now I can fill in everything in this linearization. So I can say that f of 0.1 is approximately equal to f of 0, which we just said the sine of 0 is 0, plus f prime at 0, which we said was 1, times 0.1 minus 0, which is just 0.1. So it's approximately equal to 0.1. Now, if you go ahead and put in the sine of 0.1 into a calculator, I'll throw it into Desmos here because it's pretty good to use as a calculator as well. So I'll just pull it up over here and say sine of 0.1. It's going to give us 0.0998, which is pretty close to 0.1. It would round up to 0.1, even if you were rounding to the thousandths position. So yeah, it's a good approximation. This is basically a specific example of what's known as a small angle approximation for sine x. So if I had done this not looking to evaluate this at 0.1, but just say anything, then I would say that f of x is approximately equal to f of 0 plus f prime at 0 times x minus 0. And so as long as the x value is close to 0, this is a good approximation. So f of 0 is 0, f prime at 0 is 1, and x minus 0 is actually just x. So the very quick, snappy estimation for sine x when it's a small value is just the x value. So if you're doing, for instance, well, what is the sine of 0.028? And so you would say, oh, it's 0.028, and you would be extremely close because it's 0.027996. As long as your values are small, this is going to be really accurate. As soon as your values get big, like say 3 radians, well, 3 radians, sine of 3 radians, oh, it's obviously 3 because of our linearization. So we just said that down here, oh, it's equal to x, so it's equal to 3. Let's see what it is. 0.14. That's not so good. So 0.14 is not a good estimation for 3. I suppose if your scale of numbers that you were evaluating were anything between like negative 10 million and positive 10 million, then I guess if 3 when it's actually 0.14 is really good, but it's not a good approximation for what we're interested in, what we would be interested in using it for. So that's probably a no-go there. Again, linearization is only good close to the value that you've picked to linearize around. Now, if I did want to estimate it at 3, I could use the sine of pi, 3.14. It's pretty close. Not what I was planning on doing, but let's actually do that and see how it would pan out. So again, if I say my f of x is just equal to sine x, my f prime of x then is equal to cosine x. I want to evaluate this specifically, say sine of 3 is about equal to, and it would be f at a, which would be, I'm going to use an a value. I'll write it down. A value of pi, so 3.14-ish. So sine of pi is also 0. So I probably should actually put in, without evaluating it first so I can look back and see where it came from, plus cosine of pi times, and then it's going to be x, which is 3 minus pi. And so what I would end up getting is 0 plus negative 1, and then times 3 minus pi. So now I'm not very good at this 3.1415, I guess. So I could say that 3 minus pi is negative 0.1415. And then I'll change that over with the negative sign, so it's positive 0.1415. And if I take a look at what it is up there, it's 1411 is what it gives it as. So that's a pretty good estimation. And again, all we had to do was pick a value that we are comfortable with knowing the result of it close to 3. And so pi was relatively close enough that it gives a really good approximation. All right, so we don't have to do it with just trig functions. It could be whatever. So this one is x ln x. And let's go ahead and make sure you can see it. So consider the function y is equal to x ln x. What is this function approximately equal to near x is equal to 1? So this one, the way it's worded is a little bit weird. So there's no particular value we're interested in. Instead, we're interested in coming up with a linearization function. Sometimes you can even just say that you're making a linearization function, and I'm going to call it L of x. And L of x is equal to f at a plus f prime at a times x minus a. So it's that same equation that we were just looking at. It's the starting baseline y value, and then you're adding on to that the rise, and the rise is actually just the slope times the run. So that's where this equation is coming from. Now, I used an equal sign here instead of an approximately equal to. That might seem a little bit weird or off. The reason is because the linearization is actually equal to it. So this is not the function is about equal to. I'm calling this L of x the linearization of it, and that's exactly equal to the stuff that I have after it there. So, whoa, a little bit crazy there. All right. So what I'm going to put, I'm actually going to, I do this all the time, where I write something down on a slide and I put it not in function notation, and I end up wanting to switch it just for ease of use. So since I already have the linearization written and all in function notation stuff, I'm going to just say that f of x is equal to x ln x. All right, so if that's what f of x is, I'm also going to need the derivative. Now, I haven't thought about it as a product rule, so I probably want to give myself a little bit of room. X ln x, so it would be just ln x plus x over x, which I guess it didn't need much room for. Ln x plus 1. So, all right, that's great. And what we're going to do then is I need to, it's telling us that we want to do this close to 1. Now, hopefully 1 is a value that we can evaluate pretty tidily. Let's see how it goes. F of 1 is equal to 1 times ln 1. That's going to be 1 times 0, so just a 0. F prime of 1 is going to be equal to 0 plus 1, so that's going to be a 1 there. Which means that the linearization function for values close to 1 is going to be 0 plus 1 times x minus 1 equal to x minus 1. So this is really similar to the sine one, and you might say, well, where'd the minus 1 come from? And that's just part of where x minus a, where a this time was not 0, it was 1. So we got the same 0 for the original function and 1 for the slope. So it might seem like it should give you the same result as the linearization for sine x, but it doesn't, and that's okay. So let's go ahead and attempt to evaluate this at 1.2, for instance. So the linearization is super easy to evaluate. So we just have L of x is equal to x minus 1. So L of 1.2 is equal to 0.2, and that's just all there is to it. So you put in the 1.2, subtract 1, get 0.2. Great. All right, let's see how close that actually is. So I'm going to just dip back here onto the Desmos and say x ln x, right? So that would be 1.2. Well, actually, let me just put in f of x is equal to, because I might want to do it at a couple other values, x ln x. So f of 1.2 hopefully is close to 0.2. It's 0.219. It's not bad. It goes a little bit off. I mean, if you're only estimating to the 10th, is great. Hundredths, it's okay. 2 in the hundredth position rather than 0. I mean, it's fine. But as you can tell, already getting 0.2 away from the 1 is making it a little off. Let's go 0.9 and just see how it does there. So L of 0.9, which is the linearization, is just going to be 0.9 minus 1, which is negative 0.1. And if I evaluate the actual function at 0.9, the actual function is negative 0.0948. So again, negative 0.1 is, yeah, it's okay. And relatively close to that answer there. All right, so what I'm going to do here is show you that it can be used for things that don't look very function-y, but we're going to turn it into something function-y, and it's going to work out fine. So this one says estimate the value of the square root of 33. So in this particular case, we know that root 25 is just 5. And we know that root 36 is just 6. And in grade 9, I think, you would have used like benchmarks. So you would have said something like, oh, okay, well, this is 5, and this is 6, and this is 25, and this is 36, and this is like 33, somewhere around there. Whoa, 6. So maybe like 5.7 or whatever. And that's fine. We're going to do a linearization for this particular case. I think because it's quite a bit closer to 36 than it is 25, I'm going to pick an a value to be at 36. And my function is going to be f of x is equal to the square root of x. So I know that f of 36 is equal to 6. So I already have that part down. Now, what is f prime of x? Well, f prime of x, that's like having a power of 1/2, the radical there. So the power comes down. We leave the inside alone now to the power of negative 1/2, which is 1/2 root x. I'm going to write it like that. It's a little easier to think about when you're plugging a number in. So then f prime at 36, because you need to know f at a and f prime at a. So that is going to be 1 divided by 2 times the square root of 36, which is 6. So it would be 1/12. So we are going to say then that the linearization that will allow us to kind of get the value close to 33 is going to be at, or is going to be f of a. Do you know what? I'm gonna write the linearization function first. So I'm gonna say L of x is equal to f of a plus f prime at a times x minus a. And in our case, we picked an a of 36. So this is the linearization function centered around 36. Is going to be f at a, which is 6, plus f prime at a, which is 1/12, x minus a, which is 36. All right, so allergies are coming in, throat's all scuzzy. So we get linearization is going to be 6 plus x minus 36 over 12. All right, so we want to know this thing roughly at 33. So this would be linearization evaluated at 33 is going to be equal to 6 plus 33 minus 36, which is negative 3 over 12. It's going to be negative 1/4. So this is about 5.75. Now, I might get really embarrassed here in just a moment because I can't remember exactly how accurate this one is. And I did that benchmark method and got a value of 5.7, which is pretty close to 5.75. If it ends up being better, then that kind of discounts using linearization for this particular thing, but that's okay. So we are going to say, what is this thing evaluated at 33? Oh, well, that's not too bad. 5.744. Oh, yeah, did I? I probably, when I started this out, didn't go back and say what I was doing. That's unfortunate. So it was estimate the value of the root of 33. So we're just estimating a square root. I need to get better at switching things around and realizing what it is that I'm showing and not. My apologies for that. So if we are evaluating here the square root of 33, it's 5.7445, and we had 5.75. It's a really good estimate, so I'm pretty happy with that. Better than the benchmark, anyway. couldn't estimate that well with that. All right, I am probably going to say that that's good enough for linearization, but I'm going to do a quick little chat about a few other things. So if you want to like piece out at this point, yeah, that's reasonable. I'm not going to go into much detail, and it might be more confusing than anything else because I'm just going to skim it for the next stuff. But this is technically part of that section. I don't think it's as important foundationally, so it's just going to kind of leave it at that. So this thing right here that I have at the top, dy is equal to f prime x dx, is basically the same thing as rise is equal to slope times run. Dy is known as a differential, and dx is also a differential. They are very small quantities, very, very small quantities. So what this means is a small rise occurs when you take the slope and you multiply it by a small run. This is more or less how you can read that off. So if you wanted to talk about like a linearization is not very accurate when your values of your rise and your run, or specifically your run, let's say, if the bigger your run gets, the less accurate your rise will bring you to a point where it's just not working out very well. When you take the limit as your run approaches 0, then the accuracy of your rise is basically perfect. So it's kind of the idea that's going on in this differential thing. But the way that the textbook does it is a little bit funky because instead kind of gets this idea where, okay, we'll just take the derivative of both sides of this equation. So dy by dx is equal to 2x minus 5. And then it takes this and separates it over the other side, which I don't like to do in front of my students because I have not given you context in which that would be okay. Because this, in all things that we've seen so far, really isn't a fraction, it's an operator. So it's applying the d by dx operator, the x derivative operator, on the y variable, I guess, in this case. So you would get dy by dx. And then I'm going to take the denominator of the operator that has applied on something and switch it over from the bottom of the operator that is applied on something and switch it over to the other side of the equation, which is a little bit wonky. It works out to do that, but I don't really think we are going to get into the particulars of why that sort of thing's okay. Mostly because it would probably require a different treatment in calculus in the first place. You could talk about the hyperreal number system and talk about little infinitesimals and making sure that that's laid out in a way that we feel comfortable with managing. In the time being, if you just want to think about it, hey, this is basically just, in this case right here, this is just rise over run is equal to slope, and that this is our slope equation. If that's true, then and that represents a little rise, a little run, and we move it over, then that's fine. And so that would be, I guess, my suggestion. And so if you want, it says if x was 8 and dx was 0.01, what would the value of dy be? Well, you would just evaluate that as being, hey, we punch it in 2 times 8 minus 5 times 0.01. And so I guess in that case, what, 2 times 8 is 16 minus 5 would be 11. And then so it'd be 0.11 would be the value of dy. And so that's just kind of a little side thing there. And then you can talk about, as you have changes, you can talk about the absolute, the relative, and the percent change of how your function's behaving. That's laid out in the textbook. Again, I would feel comfortable in telling you to skip it. And tolerance is kind of built into that. Newton's method is really cool. And if you kind of liked this idea of linearization and you would like to explore some other neat approximation methods, Newton's method is pretty nifty. So what it allows you to do is basically you guess at roots. So if you guess there's a root here, it's going to be like, no, there's no root there. But then you follow along a line, because if this thing has a negative slope right now, then if you follow along this line, you're going to get kind of like close to a root here. So bam, you get a root. And then you're like, no, there's actually no root there. But if you follow the slope back up this way towards the x-axis, then it kind of gets in a good spot there. But it's not quite there. And you go up here. And then you get directed back down towards there. It's going to be pretty close to where that particular root is if you apply this thing 3 times. This basically just says your next number that you get for your x value is equal to your current guess for your x value minus, and then the function evaluated at that x value divided by the slope evaluated at that x value, the current one. So what this ends up doing is it basically creates your new x value by taking your old x value and subtracting. So this, if you think about it, Newton's method here, that's basically, now if you're trying to get roots, then everything triangle wise kind of comes back to the x-axis. So your rise is the same as the y value of the function. So that's basically just rise over slope. And if we kind of play around with stuff there and say that, oh, well, but we know that slope is equal to rise over run, then what would rise over slope be? Well, if we rearrange this equation, it would be run is equal to rise over the slope. So what we're doing is we're taking our x value and then we're subtracting this kind of like the run of where the linearization would take us, and say, oh, if we do that, we get a new x value, and that new x value is going to be hopefully closer. Although you can have some crappy things happen with Newton's method, so it's not fail-proof. So you can get some, like, for instance, perfect bouncing, where you get one that like comes down like this, and then when you draw down, come back up, it actually gets you to the original value, and you just get this endless cycle of things that just go back and forth. So it's cool though, really neat, and would be worth looking into if that's something that sounds interesting to you. I'm going to leave it, I think, at that. So this would just be an example doing it. You can try it out if you want to. So try to find some roots of this thing. As you can tell, all the roots look garbo. So none of those look like they are on nice numbers. So oddly enough, because this is always easy to evaluate, because you're not evaluating the zeros, you're evaluating the at a certain position, you're just evaluating a polynomial. Now, it might be annoying to evaluate by hand, but you can find the roots closer and closer with each iteration of this. It's kind of a neat little thing to go through. Yeah, you should give it a try. Or, if you're really fancy, try to get Desmos to do this for you, and come up with a way to basically do Newton's method a little bit by hand by using Desmos. That's pretty fun. All right, anyway, take care, folks. I hope you're doing well, and I hope you had a good long weekend. I'll be talking to you soon.